Right, very well, good. Good morning, everyone. Are there some business meetings to be? All right. Morning, yeah. So it's a large subject, and I think one is also trying to give some expository lectures. So I have, although the title of my talks have been the linguistic theory, but I have barely come to that. But maybe it is for the better that I don't rush things, and at least there is something which you can take home. One of the things that I defined last time is the Steinberg representation, which I will use very soon, but I thought I will just make a comment about Steinberg representation here to a general group theoretic audience that one has a group like GFQ, and you have the Steinberg representation of this group, and dimension of this representation is equal to 2 to the power d, where 2 to the power d is the highest power of q dividing order of G of Q. And I just, and it has some other properties, but I think this property already is very striking. And then also one knows that character of Steinberg X is non-zero if and only if X has order co-prime to P. So, all these properties that we discuss here can be also considered for any finite group. And it allows you to think about whether a finite group is a Lie group. I mean, it is perhaps not true that such a fact is, so this may be not true. But still, I think it is interesting to contemplate that given G and a prime P dividing order of G, and with P to the power D maximum power which divides order of G, and there exists an irreversible representation of dimension equals P to the power D such that character of phi is non-zero if so question is if and only if G equal to G. But I am not suggesting this is true, but I am just suggesting that if you have a group and a prime and maximal power, and somehow this allows you to think somehow Lie theoretically. So one can think about this, think about so my favorite group, although I do Lie theory, is symmetric groups. Which symmetric groups Sn? So which G equals Sn P dividing order of Sn as property. So this is purely a fact in finite group theory, only about symmetric groups, and you can think about which symmetric groups are Lie groups in this sense. All right, so we began with conjecture of Macdonald. And given G prime P, there exists an irreversible representation. I mean, you know, when one thinks about GFQ, one of the properties of the prime P is that it's also, it doesn't divide the order of the group in a small measure, but it divides really in a big way. So that also needs to be kept in the back of one's mind, that the P is not dividing order of G by just power 1, but it's dividing by a high power. So but anyway, it's just a question. It is a question for this group, for primes dividing this, for which pair G comma P has a irreversible representation with this property. It would be better if the prime divided order of the symmetric group by high powers. All right, so the conjecture of Macdonald was to construct the representation RT theta, where P is a maximal torus in G defined over FQ, and theta is a character here. So this is Macdonald's conjecture asserts the existence of a representation RT theta, which is irreversible if theta is regular, i.e. of W is not equal to for all W an element of GFQ normalizing TFQ. All W belonging. And one of the main assertions of Macdonald's conjecture was that character of RT theta at an element S is epsilon G epsilon T times summation of W. So for S a regular semisimple belonging to T, for S a regular semisimple belonging to TFQ, 0 for semisimple outside TQ, and at unipotents values which are independent of theta. So I think yesterday I gave the value of the character at all semisimple elements. But here I am giving it only for regular semisimple. There is a certain multiplicity which is involved. But for regular semisimple element, it is as simple as the GL2 formula that you have seen. So you remember that for GL2, we saw that for principal series, it was sum of two characters, chi1 and chi1 conjugate. And for discrete series, also it was sum of two. And for principal series, there was a sign +1, and for discrete series, sign -1. So that sign will come up in these factors that we have. Epsilon t for the split torus versus non-split torus differs by a sign, and that accounts for the sign which comes up. Yeah, so maybe one of the key properties also is that dimension of RT theta is order of G mod order T, and this is P prime order. So this is the conjecture of Macdonald, and this is what the linguistic theory tries to prove. But I should say that one can, in fact, define more general inductions, So this induction which is there RT theta, so we talked about parabolic induction, and these ones are called the linguistic induction. So the induction is starting from any representation of Levy subgroup. So maybe so R M E phi So that RT theta, somehow this is just like that notation for parabolic induction from P to G of a representation. This is a slightly different induction, but it is an induction. Induction is a process to construct a representation of a bigger group from a representation of a smaller group. Parabolic induction or usual induction is one way to do that. It is a more complicated induction, but it is induction. And in some ways, it has many formal properties similar to usual induction. And in some ways, the usual induction provides somehow a template to anticipate what might be true also for this induction and then try to prove them. So one thing which one needs to say is that if T or M are, if T is a split torus, then of course RT theta is the usual parabolic index. So for split tori, it is the same. But for non-split torus, there is nothing usual parabolic induction, and it is the Linguistic induction. And similarly, if M is a Levy subgroup of a parabolic, P, so P is equal to N, then this R, P. So then the Linguistic induction is same as parabolic induction. The kind of, yeah, so I said this in quotation mark, these are sometimes called twisted Levy subgroups, in the sense that over FQ bar, they become Levy subgroups, but not over FQ. And it is the same story for tori. You know, any two tori are conjugate over FQ bar. So when you extend field from FQ to FQ bar, they are contained inside a Borel subgroup, but that Borel subgroup may not be defined over FQ. So for any torus T, one can write a B as T times N. That's not a problem. But the problem is that this Borel is not defined over FQ. So as far as you wanting to do group theory over FQ, it doesn't help. This Borel is defined over FQ square or FQ to the power N. And it doesn't help to do the parabolic induction, and therefore we have to resort to different methods. Looking good? RT theta is this notation, and then I use this notation, so there is a bit of a conflict of notation. One could say that this is RTG of, and theta is meant to be a character, and pi is meant to be a representation, but a character is also a representation. Looking good? So, as I said, the Linguistic induction is more complicated, very subtle, and difficult to define. But having chosen to give lectures on that, at least I should say a few words about it. So maybe I will do that. But I just want to emphasize that it's also a process of creating representations of the bigger group from representations of a smaller group. But just like parabolic induction is a bit subtle, it is not induction from P to G. It is induction of a representation on the Levy. Then you extend it on P in some ways, and then you induce. So if it was just induction from M to G, those objects are available to us. What is not available to us is the parabolic. All right. So Of course, one can just do induction from M to G. And indeed, one can ask how does that object compare? But you may ask the same question for parabolic induction. If you induce from the torus to the group G versus induced via the Borel. So in any case, there is this theorem is that you look at Steinberg of G tensor RT theta. This is same as induction from T to G of theta up to a sign. Which means that RT theta up to some correction factor is indeed this object. These are representations of the group G, and you are taking tensor product as representations of the group G. And this is a representation of G, and they are equality as representations of G. So in fact, given the knowledge of the Steinberg that we have, this allows one, mark, this allows one to think about character of RT theta at all semisimple elements since character of Steinberg is non-zero, semisimple elements. So, if you want to calculate character of this at semisimple element, then that times that is equal to this. This is the usual Mackey theory, which yesterday Shiv did in great detail. So given any induction, you understand its character theory quite explicitly. And if this character is non-zero, then this character is this upon that. And that is the formula for the character there. And it's also there for general semisimple elements. But one of the things about Steinberg that we know that on any non-semisimple element, the character is 0. And therefore, at non-semisimple element, this has no value because you are going to multiply 0 times something is equal to something, 0. And therefore, at the unipotent elements, for instance, this has no information. Yeah? Yeah, there is some analog for the Levy for sure, but I have not thought about it and I have not seen it. So, but there must be one, surely. Sorry? No, this theorem is for all tori. This is true for all tori. For a split torus, anyway, this is ordinary induction and we know everything very well. The point of the theorem is that it's true for all tori. The point I am trying to make is that the character theory of RT theta at non-semisimple elements is complicated. And you see that on non-semisimple element, the Steinberg just kills that information. So it gives you no inkling on what to do. Yeah? Good. So anyway, this is something to keep in mind because it certainly is a good theorem for semisimple elements. And it also shows that Steinberg being 0 on unipotent is put to some great use. Okay. So having constructed these representations, the few obvious questions that one would like to know is, are they irreversible? What are their composition factors? Do they construct all representations? If you vary t and theta, how do they vary? Obvious question. I mean, having created these objects, those are the most natural questions one would ask. Whether as you vary t, are you getting disjoint set of representations? So all these questions have more or less obvious and simple answers. And how are we doing with time? Yeah. So we will talk about some of them. Yeah, I was indeed thinking that I had some other remark to make. So one of the important properties of induction is that induction is transitive. Which means that induction from H1 to H2 and then induction from, let's say, H2 to G equals induction from H1 to G. And this is something which is also true in the parabolic context. And so similarly true for parabolic induction, for parabolic induction. And also it's true for the linguistic induction. So for instance, what it says is induction from M to G of induction from T to M is equal to induction from T to G. Yeah, this all makes very good sense because the notation, of course, is G contains M contains T. And so you can do, you can go directly from T to G, or you can go from T to M and then from M to G. And somehow this remark is useful because, you know, I said that for split tori, this induction is ordinary induction. But the torus may not be fully split and it may not be fully compact also, anisotropic. But you know, it may be partially anisotropic. So what you can do is that you can put that torus inside a little larger group in which it looks like a split torus. And then at least this induction will become ordinary, or you can do it other way around. You can do one induction in which it looks like anisotropic torus, and then at this step it looks like a usual parabolic induction. So yeah, partly the complication I am describing is that any torus T can be written as TA times TD. Maybe I already made this notation yesterday. Any torus is a product of a split torus and something which has no split component. So if it is totally split, then the theory is like ordinary induction. But most tori will fall in between totally split and totally anisotropic. And I'm saying that if the torus is in between, then you can look at centralizer of TD in which T will become, so to say, anisotropic torus. So somehow Deligne-Lustig theory differs from ordinary induction only for those tori which are really anisotropic. If the torus has a little bit of isotropic part, then you can kind of do Deligne-Lustig induction in two steps. One which is anisotropic induction, Deligne-Lustig induction, and one which is parabolic induction. Yeah, so Ray? Yeah. For GL2, there is not so much happening for tori because GL2 has a center. And as you know, center is not something to worry too much about. So kill center. So think about SL2 or PGL2. And then a torus is one dimensional. So either it is anisotropic or it is split. So this point of view will not help you split the problem. For anisotropic, as I am saying that I am trying to say that the Deligne-Lustig induction for tori can be done in two steps. One should understand it for parabolic induction, which corresponds to split tori, and one should understand it for anisotropic tori. And I am saying that for SL2, somehow either the torus is split or anisotropic. So therefore, this inductive step in some common sense of induction doesn't apply for SL2. But you may have a bigger group like let's say GL and GL3, and then a torus may be compact times split. And then this will apply, that you can do partly the split torus and partly the compact torus. It is like splitting the problem into, what are the main problems of a smaller kind. All right. So indeed, I am a bit rushed for time. So okay. So I just want to say that Deligne-Lustig construct an algebraic variety of course, called Deligne-Lustig variety. Variety, let's say XM, XM, or yeah, say XU. So, or P equals M times U, a parabolic of GFQ bar. Okay, defined as follows. So this is a subvariety of GFQ. So this is G belonging to GFQ bar such that G inverse times Frobenius of G belongs to Frobenius of U. So this is the variety XU, and this is an affine closed affine subvariety of GFQ bar, and they look at its L-adic cohomology, compactly supported L-adic cohomology, and the point is that XU comes equipped with an action of GFQ cross MFQ, and therefore the cohomology also has this action. Cohomology compactly supported XU carries such an action. And given any two commuting groups operating on a vector space, it allows you to construct from representations of M representations of G. That's some generality, because you will look at a representation of M and you will look at that isotypic component that will become a module for G. So generality, given a representation of G cross M, it constructs a functor from as I said, it just means that on that representation, you take a particular isotypic component for M that becomes a module for G. So, of course, one can define whatever one wants to, but the main thing is to prove appropriate properties of this functor, and that's certainly what is difficult. Okay, so d theta is irreversible if and only if theta is irregular. More generally, yeah, I'm making a usual mistake here. I'm making the usual mistake. This is not this object, but this is this. Yeah. They look almost the same. So this is the pure orthogonality kind of a relation. Pi1 times pi2 bar is equal to a number of elements in GFQ, which take the pair T1 comma theta 1 to T2 comma theta. So in particular, if the tori T1 and T2 are not conjugate, then this number is 0. And if the tori are conjugate, you assume them to be the same. And then if theta 1 and theta 2 are not conjugate under the while group, again this number is 0. And if theta 1 equals theta 2, but it is a regular character, then this number is 1. So it proves this. Plus minus, yeah. I'm saying that the second statement is stronger than the first statement, much stronger. Yeah, these are virtual representations. RT thetas are virtual. RT thetas are virtual representations, and it is equal to the number of elements in this coset, which takes this one to that. Is it good? So one of the subtleties which I was getting a little confused on the board is the following to keep in mind. So example, R T split comma 1. For GL2, it is 1 plus the Steinberg, whereas RT anisotropic comma 1, it is 1 minus Steinberg. So if you take the inner product of these two, 1 plus Steinberg against 1 minus Steinberg, you get the number 0, which is good because from split to anisotropic, there are no morphisms. So therefore, right-hand side of this equality will give you 0, and the left-hand side therefore also gives you 0, but it is not to say that these objects are disjoint. They have some common representations. Both the representations are in fact there with certain signs. Sorry, this is for GL2, yeah. And so there is another theorem which relates disjointness of the linguistic representations. And so, one can ask when are T1 theta 1 and T2 theta 2 are disjoint, meaning they have no irreversible component in common. And this brings one to interesting notion of geometric conjugacy. Which is that a pair T1 comma theta 1 and T2 comma theta 2 are said to be geometrically conjugate. If there exists a finite extension fq to the power n over fq over which they become conjugate. So more precisely what is said is that given a character of T1 fq theta to C star, one can construct a character of T1 fq to the power n by using the norm mapping. And similarly, for 2 of fq to the power n. And even though the tori T1 and T2 are not conjugate over fq, they will become conjugate over a field extension. And now one can expect that sometimes theta 1 and theta 2 may become conjugate. So in this particular example, this is indeed what is going on. Although these tori are not conjugate, by quadratic extension, you can make them both split torus, and then they are conjugate. And anyway, the character is theta, trivial character, so they are conjugate over the quadratic extension. And therefore, in this case, these two pairs are geometrically conjugate. So the theorem of the linguistic is that R T1 theta 1 and R T2 theta 2 are disjoint if and only if are not geometrically conjugate. Looking okay? Yeah. All right. So, I don't have too much time left. There is an important topic that I need to discuss. Uh, so, I said that for parabolic induction, every representation is induced from a cuspidal data on a Levy subgroup, and you have to understand subquotients of the parabolically induced from a cuspidal. That's a difficult problem, and one has to do something similar here to decompose RT theta into explicitly sum of irreversible representation and to understand which ones appear. So this is a large task, and somehow Lustig has a reduction to what are called unipotent representations. So these are representations which are constituents of RT1 or constituents of RT1 as T varies. So these are called unipotent because somehow the semisimple part of this representation is 1. That character theta is supposed to be the semi-simple part in some sense. And you look at RT1 as T varies, and you look at constituents and take the union. So this is called the set of unipotent representations. And then Lustig has one of the very important theorems in this subject, which says that representations G can be understood via unipotent representations of these. Or maybe I'm not too clear about this, so I will. So there is a certain bijection he constructs between representations in certain families with unipotent representations of certain. So in some sense, one of the really key problems, therefore, is to understand unipotent representations of a group. And for this program to be carried out, one of the key issues is to understand what are called cuspidal unipotent representations. Cuspidal. So if T is a split torus, then this is the ordinary induction. There are no cuspidal representation in that. But if T is anisotropic, it could have cuspidal representation. And somehow one of the key steps for the Lustig program is to understand all cuspidal unipotent representations for all groups. Luckily, they don't usually occur. For many groups, they don't occur, but they do occur sometimes. So maybe I will just end with this one. So cuspidal potents often don't occur, but they do once in a while. For example, for UM, they occur if and only if M is a triangular number, i.e. M equals 1 plus 2 plus D. And for the first example of a interesting representation for unitary group is U3. So U3 has a cuspidal representation of dimension equal to 2 square minus q, which was known before the work of Lustig. And SP4, I said there is this famous representation of Bhama Srinivasan, is also an example of a cuspidal unipotent. So indeed, cuspidal unipotents are somehow, I said that cuspidal representations are the building blocks, and by further reduction, cuspidal unipotents are the building blocks. All right, thank you. Sorry? There are no cuspidal unipotents. I mean, of course, there is a small clarification to be made, but GL1, the trivial representation is cuspidal unipotent. And that is something which one needs to be very clear about. Otherwise, the theory will become empty. GL1, the trivial representation is cuspidal unipotent. Somehow, yeah, by various reduction, Lustig will therefore say that as long as you understand the trivial representation of GL1, you understand everything. The rest is induction. The rest is all induction.